Yeah, so then let's start. Um, yeah, so I'm going to start with the Minkowski's form on R3 and study some level sets of the corresponding quadratic form. And I'm going to define the hyperboloid as one connected component of one of the level sets. Right? And then you see Minkowski's form is the function from R3 cross R3 to R, right? Defined by, well, on a pair of vectors in R3. You see it's almost the usual inner product, right? Almost the usual dot product, except that here, when I pair the last coordinates, I don't put a plus but a minus. Right? But so somehow, you see, I'm really deviating very minimally from somehow from what you have learned before. Right? I mean, I'm really changing very little. And that's kind of that's like a somehow that this is one of the reasons why when introducing the hyperbolic plane, I prefer to introduce first the hyperboloid, because somehow everything comes from something that really looks like something we are very used to, which is just the usual dot product. Now, yeah, so a comment is that actually with this one can model the special theory of relativity. Kind of when one sees R3, as not as, I mean, as kind of as the space-time, but kind of with two-dimensional space. Right, actually, there is some story which I read somewhere, but I don't quite remember where. So now I'm not sure if it's true or not, but because I don't remember where I read it. But so it seems that Einstein first came up with the special theory of relativity, kind of just from his kind of thought experiments that he used to make, right? Like kind of, I mean, in very clever ways. And then you see, Minkowski was one of the persons interested, and he developed this kind of the model, kind of to have an actual model, right? Like kind of when one learns Newtonian mechanics, kind of one starts modeling things with the Cartesian plane and so on. And then what I read was somewhere is that Minkowski then presented this model that he developed to Einstein, and Einstein just didn't like it. He was like, okay, no, I mean, this should all be understandable without your little model. Okay, but so something very easy. It's that this function is actually a bilinear form, so it's R bilinear, symmetric and non-degenerate, right? So by symmetric, what I mean is that when I evaluate, so let's see. When I evaluate, I don't know, in two vectors, let's say u and v, that this is equal to the other pairing, right? Yeah. By non-degenerate, what I mean is that if one vector has the property that paired with arbitrary vectors, it always gives me 0, then it's because that one was already 0. So somehow it's the only vector in R3 with the property of having pairing equal to 0 for all vectors in R3 is the 0 vector. Okay? And this you can prove. It's not so hard. However, it's really not an interior product, right? And mainly because, for instance, when you pair when you pair 0, 0, 1 with itself, you get -1. Right? So somehow, so you don't get, to be an interior product, you need that the pairing of every non-zero vector with itself be positive. Right? But as I said, 0, 0, 1 paired with itself gives me -1. So yeah, so not an interior product. Okay, but anyway, so it's an R bilinear symmetric and non-degenerate function. And so being R bilinear, I automatically have the quadratic form associated to it, which is defined as follows. It's just a function of, you see, from these pairs of variables, I take only one, right? And then what I do is Q of a vector is simply the vector paired with itself. So, okay. Right, and then we are interested in the level sets of this quadratic form, of this function from R3 to R, right? Kind of as in calculus of several variables, right? And so for each real number, I can form the level set, which is just the vectors in R3 with the property that when I apply Q to them, right, it gives me C. Right? So this is definition from calculus. And kind of the first thing, the first point is that this level set is actually a surface of revolution. Right? And this maybe I leave as an exercise. You see, if in the plane x, y, z, sorry, if in the plane y, z, right, which would be, so if this is x, this is y, and this is z, it would be this plane, right? So in order to draw the whole level set in R3, all we need is to draw the part that lives in this YZ plane and rotate the drawing. Right? So this I leave as an exercise. It's an easy exercise. Yeah, and so and I'm going to use this this property kind of to first draw things here and then just rotate to get the whole picture. Right? So now, kind of one problem. Somehow one problem is that this is somehow not presented. You see, let's say this one in a way is kind of not quite presented in the usual coordinates, so we have to perform certain rotation. Yeah, and this is to first draw these level sets in the YZ plane. So I consider this basis of the YZ plane and this other basis, which is slightly rotated, right? I mean, this basis is 1, 1 and 1, -1, right? And now for a pair of real numbers, I have, you see, a vector, a point, but written in terms of my rotated basis, this basis. We have that it belongs, that point belongs to this level set, to this one. If and only if, and then what do I need? I need the first coordinate minus the second coordinate equal to C, right? So you see first coordinate, but first coordinate now with respect to this one really. So W minus T square minus W plus T square equal to C, right? And then, well, then you see when one develops, when one expands this, W square and W square go away, T square minus T square goes away, and then this is the only thing that survives, right? Minus T W minus 2TW here, minus 2TW here, right? So minus 4, yeah. Right, and then this equality happens if and only if this equality happens, and from this equality, what I see is that that in the WT plane, that is when I compute in terms of this basis, right? So somehow when I really look at this coordinate system, I obtain a hyperbola, right? So, and then I can see, right? For C negative, let's say, I don't know, let's say C equal to -4, so that this becomes 1, and this is kind of the easiest to draw hyperbola, right? So, and then it has to be drawn. You see, if you tilt your heads, it has to be drawn here, right, and here. Yeah? So this is for C negative, right? And then for C positive, then one has to draw it here, right? And for C equal to 0, then of course, then one obtains precisely the axis, but the coordinate axis, but which coordinate axis? Well, according to the basis you are describing things with respect to, right? Okay, so all in all, what I just did was kind of I drew these hyperbolas for the distinct values of C, but somehow what I did was kind of I just did it in the by choosing the appropriate basis that allows me to really see that these are the correct pictures very easily. Right? That's all I did. So once I drew this, and I know you see something that I would like you to see is that for C negative, you see when C is negative but then tends to minus infinity, so negative but gets away from 0, so somehow the corresponding hyperbola starts getting away from 0. Right? And when C is negative but I make it tend to 0, then the hyperbola really gets close to 0. So somehow, yeah. And then for C positive, you see somehow the picture is really continuous. Right? I mean, for here I have for C positive, and then when I take C very small, then somehow this hyperbola gets like this, the picture gets kind of thin, and then when I C is positive and I let it get away from 0, the picture gets kind of somehow like thick, right? Somehow, but what I want you to visualize is that the phenomenon is kind of continuous. So I take C positive and then like positive, very positive, so the hyperbola kind of looks like very thick, and then I start moving the C, and then let's say close to 0, and then the two sheets start getting together. In 0 you get this, and then negative, and then you get away from 0, and then it starts looking like that, right? So that's something that I want you to be aware of. Yeah, and then we said that then the corresponding level set, but for the function defined on R3, is simply take whatever picture you obtained for the distinct values of C and rotate around the z-axis, right? So for C negative, then we obtain a picture like this, which I don't know, I mean, okay, the drawing is far from perfect, but where kind of the cross sections are really hyperbolas, right? For C equal to 0, well, you have to rotate these two lines, right? And then you obtain the cone, and it's the light cone, kind of the terminology really coming from special relativity. And for C positive, you really get this one sheeted hyperbola, right? So somehow the point is that the hyperbola here, when I rotate it, it really maps precisely onto the other sheet. Okay, and then a little kind of nicer picture, but of course with never mind these symbols. yeah, so there you can see kind of the pictures in a like better drawn. Yeah. And then among all of these level sets, I'm going to kind of just distinguish one, which is the level set of -1. Right? So it's for C negative, so it's this one, and then I rotate it. Right? I mean C negative because it's C equal to -1, right? And then rotated. So I have kind of these two sheets, but then I'm going to ignore one of them, and I'm going to take to really focus on only the one that the upper one, right? The upper sheet of the hyperboloid. And this upper sheet I'm just going to refer to as the hyperboloid. Okay, so this, right? When one kind of unravels what does it mean to be in this level set, well, it means that when you apply Q to the point, right, which is this, it gives you -1. Right? Okay, and then you just keep track of only the upper sheet. And of course, when we have this description, then we can say, okay, in this description, you can just solve for z, and then z becomes this square root. So you can say, okay, so m is kind of just the graph of certain function from R2 to R, which is you see xy goes to this, right? And then when you draw the graph of that function from R2 to R, you obtain precisely this. Okay. And this is going to be our first model of the hyperbolic plane. But then, as I said, I'm going to really introduce it as a Riemannian manifold. So let me say kind of very quickly what I mean. So now I have the hyperboloid, and what I want, and then in R3, I have for each point its tangent plane. I mean, for each point of the hyperboloid, its tangent plane, the plane tangent to the hyperboloid at the given point. What I want to give now is for each such tangent plane an inner product on that tangent plane, and that's and that's pretty much kind of in a nutshell what the notion of Riemannian manifold is. So it's a manifold where for each point you have an inner product on the tangent space, right? And you require something else, which is that when you move the point in your manifold, the inner product on the space kind of on the tangent space moves smoothly, right? But yeah, what does it mean to move smoothly? Okay, so for the moment I'm not going to have that discussion. What I want to communicate is that I want to consider for each point of the hyperboloid its tangent plane, the tangent plane of the hyperboloid in R3, tangent at that point, and I want to define an inner product on this tangent space, this tangent plane. Right? What's the idea? Like, why would I want to do such thing? Well, if I do it, let's say take one point in the hyperboloid, take its tangent, take the tangent plane, and suppose that I already defined some inner product. Well, having done that, I can measure lengths of velocity vectors of curves that pass through that point. Right? I mean, for each curve on the hyperboloid passing through the point, its derivative is going to be a vector living in this tangent plane, and then I can measure it if I already have an inner product on this plane. Right? So that's the idea. And then if I have such thing everywhere, I can speak of the length of a curve. Right? So that's kind of the intention, and that's what I'm headed. Where I'm headed. Okay, so this is why I'm interested in this tangent, in the tangent plane to M at a point in M, in the hyperboloid. And the first, so you see this is, yeah, so and then the claim, okay, then there's one small detail there, which is I think of that tangent plane but kind of anchored at the origin. Right? I mean, kind of when I visualize the tangent plane at a you see here, let's say, when I visualize the tangent plane at a point here, I visualize it like this. I don't really visualize it as anchored at the origin, right? Kind of translated. What I'm going to do is really I'm going to consider this one, but translated to the origin. Okay, kind of anchored at the origin. Okay, and then when I think of it anchored at the origin, the proposition is that it actually coincides with the orthogonal, with the plane which is orthogonal to the point, but orthogonal not not the way we are used to think, but with respect to Minkowski's form. And you see that's the first nice use of Minkowski's form. You see, if I'm interested in computing the tangent plane at a point, well, all you need is kind of to solve some system of linear equations, because this becomes a system of linear equations. Actually, it becomes a single equation, a single linear equation. Okay. Right, and so the proof. Well, first of all, both of them are two-dimensional real vector subspaces of R3. Right? I mean, this one is, right? I mean, and as I said, just because I'm thinking that it's really anchored at the origin. But this one as well. This one is two-dimensional. You see, it cannot be three-dimensional, because if it were three-dimensional, the form would be degenerate, because then P, you see, all of R3 would give me paired with P equal to 0, but P being in the hyperboloid is not 0. Right? So because the form is non-degenerate, this one cannot be three-dimensional, so it can only be less than three-dimensional. But then for basic linear algebra reasons, it has to be exactly two-dimensional. Right? Okay. And so knowing that they both are two-dimensional, in order to prove that they are equal, it suffices to show that one is contained in the other. Okay, so I write my point P, as I said before, right? Kind of as a point in certain graph of kind of this function. Why? Because writing it that way allows me to compute a basis of this tangent space, kind of just using the partial derivatives, right? I mean, I have the function that to xy associates this number, and then the tangent plane can be computed just in terms of the partial derivatives. And so here I have, you see, this is the partial derivative with respect to x. This is the partial derivative with respect to y. If I'm doing everything correct. Yeah, and then I just have to keep track that I'm sitting in the graph, right? So that's why I also need 1, 0, and 0, 1. Right, and then you see, then I know that this is a basis of the tangent plane. Or if you want, kind of, it can be an exercise from calculus, right? I mean, it's kind of I give you this point, this point in the graph of a function, and then compute the tangent plane. Right? And then you can compute it by exhibiting a basis. That's what I just did. So this is really an exercise from calculus. Right? And then when I take these two vectors, which are a basis, and I pair them with P, you see, I have to take this times this, so it's x plus 0 minus this times this, right? So, and yeah, sorry, this times this plus this times this minus this times this with the with the x here. Sorry, yeah, and then you see it's kind of x minus x. So it's 0. And same thing with this other vector. You pair it with via the Minkowski form with P, and so it's 0 plus y minus this times this. So this cancels, and then I get y minus y. So it's 0. So these two are Minkowski orthogonal to P. Right? So I have this, but then as I said, both of them are two-dimensional, so they have to be equal. Okay. And now kind of the theorem that makes everything work, right? Which is that for each point in the hyperboloid, when I consider Minkowski's form itself, but restricted to that, to this two-dimensional space, what I obtain is an interior product for that tangent plane. Right? So Minkowski's form is not an inner product for R3. Right? We just saw it. But on each of these two-dimensional spaces, which are not the whole R3, it is for each of them. Okay, so right, and then let me come back to the next statement later on. It says something about smoothness. Right. So first, that the restriction of this to the tangent plane is always an inner product for every point. So first, I mean the Minkowski's form is certainly, we already know that it's R bilinear and symmetric, right? So this one is R bilinear and symmetric. Okay. Now take any point and a non-zero vector. So what do I know immediately? That, well, what I know is that P and V are Minkowski orthogonal. So I just write what it means to be Minkowski orthogonal, right? And this is just from the previous proposition, right? To be tangent is to be Minkowski orthogonal. Okay, and now I'm going to use Cauchy-Schwarz inequality, which I just wrote here to remind you, right? Which is for any real vector space with an inner product, I have this inequality. And so I mean, I don't know yet that this one is an inner product. So what I'm going to do is I'm going to use Cauchy-Schwarz inequality, but for something that I already know is an inner product. And that is simply the usual inner product in R2. Right? So the usual inner product in R2, you see the norms squares precisely look like this, right? X squared plus y squared for this, and then a squared plus b squared for the other one. And then according to Cauchy-Schwarz inequality, this is greater or equal than this other, which is the square of the dot product. The square of the dot product of, you see, x times a plus y times b. Right? So here I'm using Cauchy-Schwarz inequality for the usual inner product in R2. And then, you see, using this equality, what I have is that this square is equal to ZC square. Right? So here I'm already using Minkowski orthogonality. And then you see C square, C, you see P is in M. So C is this square root of something A squared plus B squared, right? And more precisely, you see I have A, B, and this is C. Right? So C is square root of A squared plus B squared plus 1. So I substitute this C, not this, right? There's no square root because it's square, right? Okay. And now here I know that P is in M, which means I know that A squared plus B squared minus C squared is equal to minus 1. So, sorry. This I wrote this indication precisely for the substitution I already made. Sorry. Right, and here I just distribute Z squared. Right, and what do I conclude? Well, I conclude that you see, the point is that here, this is greater or equal than this, but here I have this A squared plus B squared, which also appears here. So I can move this to the left, right, and then extract A squared plus B squared as common factor. And what I obtain is that such thing is greater or equal than this Z2 square, that this Z square. Okay. So, you see, I took my non-zero vector. What I want to prove is that paired with itself is strictly positive, because that's part of the definition of being an interior or inner product. That for every vector paired with itself, it's positive. So that's what I want to prove. Okay, and so my vector is this one. And I have two cases. You see, if Z is not 0, then this is positive. And I know this is positive. Hence, this has to be positive. But this is precisely V paired with V. Now, what happens if Z is actually 0? Well, if Z is 0, you see, V paired with itself is x squared plus y squared minus 0. So, but x squared plus y squared has to be positive because V was not 0. So either x or y is positive. So either x or y is non-zero. So in any case, what I obtain is that V paired with itself is always positive. And so I obtain that this is an interior product. So I would still have to check non-degeneracy. Yeah, right. I check this, but you see, I would still need to check that GP TPM cross TPM to R is non-degenerate. Not M. Sorry, to R is non-degenerate, and then you can say, okay, but somehow you know that Minkowski's product is non-degenerate. And then I would say, okay, yes, but you see, now I'm really talking about restriction and not the whole Minkowski product, not the whole Minkowski form. So I leave it as an exercise. Somehow the point is that if these were degenerate, you see, I would be able to pick a point here, so that to pick a non-zero vector here whose pairing with everything here is 0, and then somehow right, and then yeah, and then I would need kind of to extend to sort of kind of outside. Right. Sorry. But that cannot be the case, right? Because paired with itself is positive. Okay. Yeah. So okay. So actually this non-degeneracy is already part of this statement, which we already did. Okay. And now notice. So you see, I have this. For each point P, I computed already a basis of the tangent plane. Right? So here it is. Right? The basis, of course, each vector of this basis lives, of course, in R3. 1, 2, 3, of course. But it itself, but the space is two-dimensional, and I have an inner product on that two-dimensional space. And then I can compute the matrix of this inner product in terms of this basis, and then it has to give me a 2 by 2 matrix, right? Because the space is two-dimensional. Right? So So what I mean is this, that here I have this first basis vector. I don't know. Let's call it v1, and let's call this second basis vector v2. And then, since I have this the inner product, this inner product on the tangent plane, I can compute this matrix, which by definition, the definition is that this is GP of v1 v1, GP of v1 v2, GP of v2 v1, and GP of v2 v2. Right? So all I need is kind of is to take my two vectors and consider all possible pairings. This with itself, this with this with this, which is going to have to be the same because it's symmetric, and this with itself. And what I obtain when I do that is this matrix. Is this matrix where, you remember, P was written as ABC. So what I see is that P was written as ABC, and then, and C really can be put in terms of A and B. Right? And then what I see is that the entries of this matrix, each of them defines a function of class C infinity on AB. I mean on the two coordinates. Right? Just because the denominator here is always greater or equal than 1. Right? And that's what I mean by what I said, that the inner product I have varies smoothly when I make the point vary. Somehow here I'm making P vary, right? And I'm actually making not quite P, but its projection in the xy plane vary. And when it varies, the inner product varies according to how these entries vary, and that variation is smooth, is of class C infinity. So under Minkowski's form, the hyperboloid becomes a Riemannian manifold. Okay, so as I said, one of the things that this is going to allow me is whenever I have a curve of class at least C1 on the hyperboloid, when I take the derivative of that curve, which is kind of at each point gives me the tangent vector at the curve. Each of these tangent vectors, I can measure them. I mean, I can just pair them with themselves with Minkowski. Right? So I know the length of each of these vectors, and so I can integrate. And so I can play the game of defining the length of a curve. Okay. Now, I'm interested in studying the isometries of the hyperboloid. And so now there's going to, there really are, strictly speaking, one has to distinguish two types of isometries. One is the metric isometries, and the other is the Riemannian isometries. Right? So I prefer to, I mean, in the end, at least for the hyperboloid, it really is the same to speak about the isometries as a metric space and about the Riemannian isometries. So in this case, it's the two notions really coincide. But I prefer to take the viewpoint of Riemannian isometries. Okay, so if I have my two Riemannian manifolds, and if you still have a hard time thinking about a Riemannian manifold kind of in full generality, just think about the hyperboloid with Minkowski's form, right? I mean, Minkowski form on each tangent plane at the hyperboloid. And then suppose I have a function, let's say from the hyperboloid to itself, right? And then I'm going to say that this function is a Riemannian isometry if it is a diffeomorphism, and for every point, let's say in the hyperboloid, and every pair of tangent vectors, both of them tangent at the point, the following happens. And then this formula is actually, it really means something simpler than it may look at the first sight. So I have my function, I have my function f, from which I'm requiring already to be a diffeomorphism. Right? So let's say I have my function f. Yeah, so I don't know, let's say that I have m, if you want, and just think of the hyperboloid, I have n, and then if you want, again, just think of the hyperboloid, and I have my function. Right? And then whenever you give me a point here, the derivative of f takes the tangent plane. Let's say that this is p, and let's say that this is f of p, right? This point, and so the derivative of f takes the tangent plane at p to the tangent plane at f of p, right? And then here I have Minkowski's form that I can apply with which I can pair the two tangent vectors. Or I can take the image of those vectors under their derivative and see how they are paired here. Right? So see how they are paired here. Right? And then I say that f is a Riemannian isometry if that pairing coincides precisely with the original pairing here. So they paired here, their pairing here coincides with the pairing between their images. And this is everywhere, right? For every p and for every pair of tangent vectors. which, if you think about it, what it tells me is f is a diffeomorphism. So kind of I require that it be a diffeomorphism so that I don't have to worry about, like, okay, the derivatives, until which order are they really defined or whatever, and then the condition that the pairing that those pairings really coincide. It's really, you see, it's that kind of that somehow when I see what it does at the level of tangent space of tangent planes, it really measuring a vector before or after, it gives me the same. The length of a tangent vector is that f preserves the length of a tangent vector. That's what somehow in the end it really means. Although kind of to see what one has to write may be a bit intimidating at first. Right, and now just diffeomorphism, just to be clear, what do I mean by diffeomorphism? I mean a bijective function of class C infinity whose inverse is also of class C infinity. Right? So I require it to be not only the function C infinity, I require the inverse to be C infinity. Yeah, and so now we, of course, as I said, I want to study the group of Riemannian isometries of the hyperboloid, Minkowski's hyperboloid. And these are given in terms of the Lorentz and proper Lorentz groups. So some considerations. I mean, somehow it is always a good idea to try to present your groups as matrix groups. For instance, translations of the Euclidean plane, like consider just forget a little bit about the hyperboloid, right? I mean, forget about just forget about the hyperboloid, and then just consider the translations of the Euclidean plane. They form a group, right? I mean, translation by beta followed by translation by beta prime is translation by beta plus beta prime. Right? The inverse of a translation is another translation. So translations just by themselves, they form the translations of the Euclidean plane form a group. But of course, when I ask, okay, among translations of the Euclidean plane, which ones of them are linear? Like only the identity. I mean, because kind of by very definition, if the translating vector is not zero, it just cannot be linear. However, thinking of the Euclidean plane as sitting inside C squared at height 1, and here it's at height 1. You see, kind of instead of thinking of the Euclidean plane as our vector space, but rather as an affine plane sitting at height 1, actually a translation then simply becomes multiplication by this matrix. Right? And so what I'm saying is that translations the group of translations has a realization as a certain group of matrices, and why is that good? Well, because I can at least recur to linear algebra whenever I need it. Right, and then actually what I just said is valid not only for translations but for all isometries of the Euclidean plane. Kind of for all bijective functions of from the Euclidean plane to itself that preserve the Euclidean distance. Again, they form a group. They are the vast majority of them is not a linear function, but it is possible to realize the group as a group of matrices, kind of by a similar principle of seeing the plane kind of sitting at height 1. Okay, so this is an exercise. Right, so somehow following a similar philosophy of trying to see the groups we are interested in as groups of matrices, what I'm going to define is, you see, I'm going to see that I'm going to consider the matrix of Minkowski's form. Again, Minkowski's form is a bilinear form, right? So I can take its matrix with respect to any basis. Right? So I just consider the standard basis of R3, and with respect to the standard basis of R3, I can just take the matrix that represents Minkowski's form, and what I obtain is this. Right? I mean, this is the pairing of the first standard vector with itself. When I pair the first one with the second one, the first one with the second one, first one with the third one, right? And then just 0, 0, 1 paired with itself is -1, right? Okay. So, okay, and then what we're going to see, what we're about to see is that the Riemannian, we're going to realize the Riemannian isometries of the hyperboloid as subgroups of the group that preserves this matrix. Right? So we define the Lorentz group. O to 1, this 2, 1 is precisely because of this plus, plus, minus. And it's the group of all matrices in all invertible matrices of size 3 by 3 that preserve the form. Okay? And then I define the proper Lorentz group as the set of all of those here that actually have determinant 1. Okay? And then the first exercise is that actually every element here has determinant 1 or -1. So somehow this one is not so much bigger than this one. And actually what this should be telling me is that somehow the index of this one here is 2. Okay, and then something that that more or less by now you should be expecting, which is some characterization. Right? I'm about to give some characterization, although I'm still stopping short from having a final statement that says preserves the hyperboloid. Right? That this I'm not characterizing that yet. But anyway, if you give me an invertible matrix of size 3 by 3 with real entries, the following are equivalent. It preserves Minkowski's form, right, for everywhere. Something that seemingly weaker, which is you don't have to consider all pairings of arbitrary vectors with arbitrary vectors, but rather just pairings of vectors with themselves. Right? And then A preserves the pairing of anything with itself. Something seemingly weaker, which is actually you only need to check that that on these 3 level sets that each preserves these 3 level sets. Right? And so recall, let me So recall the level sets. So one of them is for C equal to -1. The level set is it's the hyperboloid, but here I have to draw the two-sheeted hyperboloid because I'm taking the whole level set. And then for Q equal to 0 is the light cone, kind of both for the future and the past. Right? Okay, so the drawing is really terrible, but and for C equal 1, it's this one-sheeted hyperboloid. Right? And so what I'm saying here is that this matrix A maps the pink surface, the pink surface to the pink surface, but of course it could switch. Right? That's perfectly possible. And even if it doesn't switch, it could be that it reflects. So even preserving the pink part may not be like completely well behaved, but okay. But that's part of what I'm saying here. And it also preserves the blue, the cone, and it also preserves the red. But kind of preserves just sending to themselves, right? And then the next one is that it's enough that it sends pink to pink, pink inside pink, blue inside blue, and red inside red, so that it actually preserves each of them bijectively. And finally, preserving this matrix. Right? And somehow you see this condition is the easiest to check. I mean, for this condition, you really have to just perform two matrix multiplications, right? And check whether this happens or not. So somehow all of this is somehow like a more conceptual, and this is okay. This is what you actually end up checking, right? in practice, let's say. Yeah, and then the proof. You see, I mean, one implies two. Well, it's obvious, right? I would say one implies two. It's obvious. Two implies one, so I'm going with the equivalence between these two first. So you see, this polarization identity tells me this, right? For the quadratic form, and what it tells me is that I can compute this pairing completely in terms of the values of Q. Right? So if A, if I know 2, so that I'm free to write or not write A inside the parentheses of the Q. Well, here I'm free to write A without changing the value, right? And then A is linear, so A here goes inside, right? And then I can just go back, and then you see once I'm here, I say okay, so by the very same polarization identity, that's the same with A, right? So kind of the crucial thing is really this identity. So we know now that we know this equivalence. One if and only if 5. Well, for instance, that one implies 5. I would say is really obvious because because if this happens, then in particular for the standard basis vectors, right, this happens. But for the standard basis vectors, the pairings are precisely the entries of this matrix. Right? So I would say 1 implies 5 is pretty much, just specializing, and from this equality for all possible vectors, just specializing for when the two vectors are standard basis vectors. And the converse is, well, it's linearity. So I would say that now we have these two. 2 implies 3. 2 implies 3. Well, it's obvious, right? I mean, if the value of Q doesn't change when I apply A, well, when I apply A, the value doesn't change. Okay. So 2 implies 3 is obvious. 3 implies 4 is obvious. Wait. Sorry, 4 implies 3 is obvious. But yeah, but so let me go to 3 implies 2. Right. 3 implies 2. So right, so 1 second. Right. So what is not completely obvious from 3 implies 2? Well, that here you see, because I mean, you can tell me, look, this precisely says that A doesn't change the value of Q, right? That A applied to something that gives you C gives you C. And then you can say, yeah, and then of course 3 implies 2. But the problem is that here this would be, I would be assuming this only for these 3 values. And this one is really for all possible values of C. So how do I extend from just knowing for these 3 values? How do I know that for all values of C the same happens? That's the part that is kind of not quite obvious, although it's not so hard, because somehow the point is that Q is quadratic, right? I mean, Q of lambda V is lambda square Q of V. Right? I mean, recall that Q of x, y, z is x squared plus y squared minus z squared. So it's clear that when I have lambda here, it comes out with a square, right? I mean, and here this is just the linearity of multiplying by A, and so the rest is really just kind of the straightforward computation. To see, you see, in the end, you see, I can go with something. You see, C divided by absolute value of C is 1 or minus 1 if C is not 0. And what I do, the trick that I perform here is that this is equal to this, and then I can cancel C, and then Q of AV is Q of B. Right? But kind of just from this equality. Okay, so that's 3 implies 2, so and 2 implies 3, as we said, is obvious. So I have this. 2 implies 4. 2 implies 4. You see, if I know that Q of AV is equal to Q of B for all V's, and I want this kind of bijectively, right? Kind of, I want not only that preserves that something that gives you C, that A of something that gives you C, not only that, but kind of that anything that gives you C is A of something. So, right. So now from 2, which is precisely that A that A of something that gives you K gives you K. So you see, the point is that since A is bijective, for different values of for different real numbers, when I look at the corresponding level sets, how to say, how I want to say it in that kind of in the clearest way possible. So for any real number k, so this is the k here. For every real number k, I know that a of the level set of k is contained in the level set of k. If I change from that k to another real number L, I know that for this other real number L, the A of the level set is this other level set. But these two level sets are disjoint. Right? I mean, if I change the real number, the level set really is completely disjoint. Right? And that's simply because Q is a function. So this means that A, you see that whenever I take a point here, it comes from something under A, but that something cannot live somewhere else, because then it would go somewhere else. It has to live in the same place. And so in the end, the real reason is just because Q is a function. So when I take 2 points in the column in the image, 2 different points in the image, their inverse images are completely disjoint. That really is it. So I have this 2 implies 4. Right? And now 4 implies 2. You see, I mean, somehow I already did the hardest part, which is, just from knowing this, how do you know the equality? Right? So I did the hardest part, and then this is obvious. And so now I have equivalence, right? Okay. And then the immediate corollary is that when I just take the upper sheet, right? I mean, I just take the hyperboloid, but only the part I'm interested in for hyperbolic purposes, and I apply an element of the Lorentz group. Well, I know that for c equal to -1, you see, I have A preserves the level set. Right? So what I have is that for the elements of the Lorentz group, they preserve kind of the pink part, but unfortunately the pink part has 2 components. So I cannot say that every element here preserves M. Yeah. Let me go over it again. Okay. So again, if I assume 2, right? I mean, I know that A preserves that. You agree with this, right?
Yes.
Yeah. Okay. Now, right. So this means that for each level set, I don't know, A of the level set is contained in it, right? Now, if I change the level set, again, A of this new level set is contained. A of this new level set is contained in the new level set. Okay, but you see, so let's see. So this would be Q inverse of K, and then let's say that this is Q inverse of L. I hope it's clear enough. But you see, K is different from L, so you see everything here under Q goes to K, so it cannot go to L, right? And everything here under Q goes to L, so it cannot go to K. Right? So this means that that the intersection is completely empty. The intersection between the blue one and the green one is completely empty. Right? Okay, now take a point here and take A of it. Right? Sorry. No. Take a point here. Yeah. You know it's A of something because A is bijective. Okay, it's A of something. I don't know. Right. Now that something has to be in the green set. If it were not in the green set, it would be in some blue set.
So every point is in some level set?
Right.
Ah, right.
Yeah,
okay.
yeah.
Yeah, okay, that's
Uh-huh.
good.
Uh-huh.
Yeah.
And so it cannot be in any blue set. It has to be in the same. Right? Because otherwise it would go to the blue one. Right? Yeah. And so right, and so this this has to be A of something, that something has to be again in the same set. So I have equality. Okay. So now I ran out of time. So you see now. So I just kind of just to conclude. So certain group of matrices that I defined, just as a group of matrices preserving Minkowski's form, is really related to preserving the hyperbolic, the hyperboloid. Right? I mean, if you think about it, yeah, it has to be. Right? And one of the things now I want is to determine which ones really preserve it. Right? And kind of exclude the ones that don't preserve it. And then we're going to see that precisely because they preserve the form, you see, the form restricted to any tangent plane is an inner product. So here you see you are actually seeing the formula that is the matrix itself preserves the inner product on any tangent plane. And you see, and a matrix is the derivative of multiplying by that matrix. So this is an equality that is not only for A, it's for the derivative of A. But we will speak about this next time.